Hello, welcome to tonight's live session. I had to reschedule this one because something came up later in the evening. So I'm going to be going over the basics of 9.6, which is counting principles. So 9.6 covers solving simple counting problems, using the fundamental counting principle to solve counting problems, using permutations to solve counting problems, and using combinations to solve counting problems. So the fundamental counting principle says, let E1 and E2 be two events. So we use the letter E to represent an event. The first event can occur in m different ways. After the first event has occurred, the second event can occur in m2 different ways. The number of ways that two events can occur is m1 times m2. So if you are looking at two things happening and you want to count all the probabilities that those two things can happen, you multiply the total ways for each. And this can be extended to more than two events. So if with an example here, how many different license plates can be formed with 3 different letters of the English alphabet in any order? So how many possible combinations of license plates from 3 letters? So we're going to be just using 3 different letters. So I like to just kind of draw lines to indicate there are 3 spots that we're filling in. And so there are 26 letters in the alphabet. So I have 26 choices. And it says they have to be different letters. So once I use a letter, I can't use it again. So in the second spot, I now have 25 choices. And then in the third spot, I now have 24 choices. And so you multiply these together, 26 times 25 times 24. So when you do that, you get 15,600. So there's 15,600 possible different license plates of 3 letters using 3 different letters, and they're different, so you're not repeating those letters. So that's the fundamental counting principle. It's just you're looking at the number of choices you have, and then you're multiplying them together. If we were allowed to repeat letters, then you would have 26 times 26 times 26. Now let's look at permutations. So the definition of a permutation of n different elements, so like for letters, you have 26 different letters, is an ordering of the elements such as one element is first, one is second, third, and so on. So these are ordered. So order matters. So for example, A, B, C is considered different from B, A, C, because the order is different even though the letters are the same. So the number of permutations of n elements is n times n minus 1, and so on. So you're just multiplying by 1 less. It's like what we did with the letters, except we stopped after 3. The exclamation point is called the factorial symbol. So this is called a factorial, and it just means you're counting down. So 5 factorial will be 5 times 4 times 3 times 2 times 1. So for an example, how many permutations of the numbers 0, 1, 2, 3, and 4 are possible? So how many ordered possibilities are there? So we've got 5 choices here. So n is equal to 5. So that means we have 5 factorial choices, which is 5 times 4 times 3 times 2 times 1. Some calculators have a shortcut button for the factorial, some don't, so you'd have to figure out and look up your calculator. But 5 times 4 is 20, times 3 is 60, times 2 is 120. So this is equal to 120. So there are 120 different permutations, ordered sets of the numbers from 0 to 4. Now we can have subset permutations, so where you're not going through every possibility, you're doing a subset. So this is like what we did for the license plate. So this would be our license plate. We're doing a permutation. We're looking at all the different orders of 26 letters, but we're only picking 3. So it's a subset of 3. And so we've got this formula here, which is usually in most calculators have this. Basic calculators, scientific calculators do have a shortcut for this. It's NPR, where N is the number of choices and R is how many sets that you have. And so this formula is this factorial. So for the license plates that we have, it would have been 26 permutation 3. So we chose 3 out of 26, and then we're looking at permutation, so we're looking at the order there. And so if you did that formula, it is 26 factorial over 26 minus 3 factorial. So I'm going to just show you how this works. 26 factorial. So I'm going to just, I know the red doesn't look good on the green, but bear with me. 26 minus 3, let me erase that actually, so 26 minus 3 is 23. So 23 factorial is 23 times 22 times 21, and so on. So everything, you can cancel out the common factors here. 23 on the top, 23 on the bottom, 22 on the top, 22 on the bottom. And so you're left with 26 times 25 times 24, which is what we did on that slide here. So that was a permutation where we're looking specifically at 3 choices. So in green here, and I'm going to just switch my ink color to make it clear for the example here in green, we have a pool of 12 candidates, and the offices of president and vice president and secretary and treasurer need to be filled. So there are 4 offices here. So our subset, so our total number is 12, and the subset, which is 4. And how many different ways can the offices be filled? So the order matters because putting somebody as president is different than selecting them for vice president. So that's why we're using a permutation. So the notation is 12p4, which is 12 factorial over 12 minus 4 factorial. My line is a little bit too long there. So that's 12 factorial over 8 factorial, which the 8 factorial part will count. So that's 12 times 11 times 10 times 9, which it makes sense because once you've chosen somebody for an office, they can't choose again. So you initially have 12 offices, 12 choices, then 11 choices, then 10, then 9. So when you multiply that all out, you get 11,880. So if your calculator has the button for 12p4, then you could verify that that's what you get. So I have the TI-30X2, and there is a button that says PRB, and that is where these things are stored. So if you hit PRB, you get NPR, NCR, and the factorial button. And so the way it works on my calculators, I have 12 first, then I hit PRB, and then the NPR button, and then I hit 4. So I hit the button in between there. So where the P is, that's where I hit my button. And that gives me 11,880. Otherwise, if you don't have a calculator, you can figure it out this way like I just did, where I took the factorials, canceled things out, and then you could do the 12 times 11 times 10 times 9. Now, let's look at something a little different, distinguishable permutations. So distinguishable permutations means that we have to make sure the combinations are different. So this matters when you have things where you have like repetitions, and it doesn't work so much with numbers, but we're going to have letters in this example here. So It says, in how many distinguishable ways can the letters in Indiana be written? So we have to say distinguishable ways because there are some repetitions. There are two A's, there are two I's, there are two N's. And so one N is exactly the same as another N. If we did a regular permutation, then it would pretend that the N's are two separate N's, but they would form the same combination because they're actually identical. So our formula is slightly different. So the number of distinguishable permutations of n objects is the total that you have, n factorial, divided by the factorial for each set of objects, the combinations for each set. So this will make much more sense with an example. So we have Indiana. So there are two I's. We have N. There are two N's in Indiana. There is one D, and then there are two A's. So if we use the formula, so there are 7 letters here. So N is equal to 7. So it's going to be 7 factorial. And then you take each of the mini groupings. So there are two I's, so that's 2 factorial. Then 2 N's, that's 2 factorial. 1 D, so that's 1 factorial. And then 2 A's, so that is 2 factorial. So you basically take the factorial for each little mini subgroup and how many of those there are. So 7 factorial, if you have the factorial button on your calculator, or you can just do 7 times 6 times 5 times 4 times 3 times 2 times 1 or whatever, that comes to 5,040. And 2 factorial is 2 times 1. So this is just going to be 2 times 2 times 2. So 2, my pen is having issues here. It doesn't want me to write. 2 factorial is equal to 2 times 1, which is just 2. And 1 factorial is just 1. So we just get 8 in denominator. So 5,040 divided by 8, we get 630 possibilities, 630 distinguishable ways that you can have the letters in Indiana. If they don't have to be distinguishable, then we would have 5,040. We'd have 7 factorial. But because some of the letters are exactly the same, a lot of those would look the same. So that's why there's 630 distinguishable ways. Now the next type of counting is combinations. So permutations are where the order matters. Combinations are where order does not matter. So order does not matter. So that would be like if you have a group of people and they're sitting in some chairs, the order that the people sit may not matter. It doesn't matter where they sit. So that would be how many possibles where the order doesn't matter. So that's a combination. So the symbol that you have NCR, which usually is read N choose R, and it's very similar to the permutation formula, except that you're also divided by R factorial. And so it's basically a permutation divided by R factorial. So an example here, to conduct an experiment, researchers randomly select 5 students from a group from a class of 20. So the total that we can choose from is 20, but we want 5. So our R is 5. So how many different groups of 5 students are possible? So if we did a permutation, that would say the order that students are matters, and that consists of a different group. But that's not true in reality. The order that people are picked for a group, you still have the same people in the group. So that's why we want a combination, because the order that they are chosen in does not matter. So this would be 20C5. So that's 20 factorial over 20 minus 5 factorial times 5 factorial. So you could use your calculator to do this. If I want to show you how this works, like if you want to use the canceling property, So on the top, 20 factorial is 20 times 19 times 18, and so on. 20 minus 5 is 15. So 15 factorial is the same as that 15 on top, so those would cancel. And then we have 5 times 4 times 3 times 2 times 1. So you could treat this like a fraction where you can start dividing things. So 5 times 4 is 20, so you can cancel those out. Let's see, 3 goes into 18, so that would leave you with 6. 2 goes into 6, so that would leave you with 3. And so it would really be 19 times 3 times 17 times 16 if you want to try to simplify it. But I recommend just finding a calculator that can do this for you. Just find a calculator and make sure you know how to use your calculator so that you can calculate this out. So when you actually do this math, you go, let me pull out my calculator. So again, just like the permutation, I have to do 20 first, and then I hit my NCR button, and then I need to type in 5. So I get 15,504. So that is how many group combinations there are from 20 different students if you're having groups of 5. Now here's another example, and this is actually my last example. And then the next live session I will be doing will be on probability. So Powerball. The game is played by drawing 5 white balls out of a drum of 69 white balls, numbered 1 through 69, and 1 red Powerball out of a drum of 26 red balls. So those are going from 1 to 26. The jackpot is won by matching all 5 white balls in any order and the red Powerball. So it says find the possible number of winning Powerball numbers. So to win, order does not matter. So we have white balls are 69, and we only need 5 of them. That's a terrible 69. So it's going to be 69, choose 5. But then you also need to match the red ball, and there are 26 possibilities for the red ball. So we have to multiply that by 26 because there are 26 choices for that 6th spot. And so then on the calculator, 69, choose 5. This is, I've got this written out, 11,208,513, then times 26. So you multiply those, we get 292,201,338. So that's how many possible winning Powerball numbers there are. So your chance of winning the Powerball is 1 out of that number. So that's actually going into 9.7, which is probability. But if I do 1 divided by 292,201,338, it's, goodness, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 zeros after the decimal point before your first number. So that is a very, very tiny probability. This is why I don't play the lotto, because I look at the math and I say it's not worth it. So there are a lot of possible combinations of winning the Powerball, and you just need to do 1 out of those possible combinations in order to win. So now the second part here says find the possible number of winning Powerball numbers when you win the jackpot by matching all 5 white balls in order. So let's say instead of just matching all 5 of the white, you had to do it in order. So that would be even harder because now the order matters. So this would be a permutation. So it would be 69, if my pen would let me write, 69 P5 times 26. So there's going to be more combinations because now the order matters. So this comes out to 1 billion for 1,348,629,560 choices or possibilities to get them in order times 26. And then when you multiply that, that comes out to 35,064,160,560. So it's even harder to win, or at least to get them all in order, because there's more possibilities when order matters. So that is all the examples that I had. Now I know that we did have someone join a little bit late, but did join. So Robert, do you have any questions? I know you came in a little late, but you didn't miss too much. Do you have any questions?
No, I think I'm good.
Okay. Yeah, I think the biggest issue with this section is just knowing whether you have to use a permutation or a combination. And I don't know what kind of calculator you have. I'm going to briefly stop sharing to show you mine. So this is the one that I have, the TI-30X. And so my button to get these symbols are right here where it says PRB. So as long as you know how to use it on your calculator, just use that button to figure that out rather than trying to do it by hand, and that should make things easier.
I've actually found a download an app, a free app in the App Store. Has the same feature. Works great.
Perfect. Yeah. So as long as you know how to use it, I definitely don't want you guys to try to sit here on your calculator, go 30 times 29 times like that. That would take too long. So. All right. Let's see. And where's my? I'm gonna bring up my calendar to see, because I know I have another one scheduled on 9.7. I just looked at when I was doing that. I think I'm doing that on Monday. Let me just double check by pulling up my calendar. Yeah, so Monday it's 11 a.m. It's that was the only time I could fit it in my schedule. But Monday at 11 a.m. I'll be doing 9.7, and then I will be doing a question that's similar to one that's on the homework for this week. I don't know if you've looked at the homework, but there's one about a deck of cards and finding the probability of getting a certain hand. And that one, a lot of people really struggle on that one. And so I'm going to be doing an example similar to that one in the live session on Monday. So that is definitely one to watch. If you can't join it live, you can watch the recording. So, all right. Anything else that you have for me? Any questions or anything?
No, I think I'm good. I appreciate it.
All right.
Sorry, I was late.
Yeah, sorry, go ahead.
Oh, I just said sorry, I was late.
Oh, yeah, that's fine. I know I had to change the time because I realized, oh, wait, the debates are tonight. I really want to watch those. So I was like, okay. Yeah, I'm going to be doing a lot more live sessions for the second half of the class, because that's usually the things that start getting harder for people. So I know the past couple of weeks I didn't do any because they really usually pretty straightforward, and I've been noticing that on the grades too. The grades are much better than they were before. So, but the second half of the class usually gets more difficult. So there's definitely going to be more live sessions to come. So, all right. Well, I'm going to pop off here and let this video process so that I can get that posted, and hopefully I will see you at my next one.
Thank you.
You're welcome. Have a great night.
You too. Bye.
Bye.